So next we're going to look at properties of permutations. And as our main example, we're going to talk about what's called left to right minima in permutations. So this is a parameter of permutations, so I want to talk some about the general approach that we use for analyzing parameters. And we talked about it last time for trees. So we talked about leaves in random binary trees last time. So we're going to use the cumulated cost approach because we can use the symbolic method in a very straightforward manner. Recall that we're going to define generating functions for the counting sequence and for the accumulated cost. And then we're going to have a construction, and the construction will give an equation, a generating function equation for the cumulated generating function. And then we're going to either solve to get an explicit formula or find another way to extract coefficients to get the counting sequence and the cumulated cost. And then we divide the cumulated cost by the counting sequence in order to get the expected value. And we did that for leaves and binary trees last time. And that's the general approach that we typically use in analytic combinatorics to analyze parameters. Now for permutations, there's a small trick. There's also a small trick for strings we'll see next time. And so first thing is we're going to use exponential generating function for the cumulated cost. So, and it's exponential in the size, so we're going to consider the generating functions of the form b of z equals the sum over all permutations, whatever the cost of the parameter that we're analyzing, times z to the size of the permutation over the size factorial. And that's, again, if you group them by their size, that's z to the n over n factorial times the cost. So exponential cumulative generating function. Now, what we'll do is treat that as an OGF to get the expected value out directly. It's a little, so B sub n is the total cumulated cost. That's the total cost for all permutations of size n. B sub n over n factorial is the average. This works because n factorial is both the normalizing factor and it's the counting sequence. So really this is shorthand for n factorial times coefficient z to the n of b of z is the total cumulated cost. N factorial is also the counting sequence. So if we just extract the coefficient of z to the n, we get the average for permutations. So that's what we're going to do, is we're going to work with an exponential accumulated generating function, but then when it's time to extract coefficients, we'll just extract coefficient of z to the n and immediately get the average value of the parameter. The application is an elementary method known as selection sort, and it takes quadratic time for randomly ordered permutations, but it's the method of choice in some situations. For example, when records are large, and you can read about that in the algorithms book. And it's a very simple algorithm that goes through from left to right. The first thing it does is find the minimum element in the permutation, exchanges that with the first. Then it finds the minimum in what remains and exchanges that with the second, and so forth. So first question is how many times there's a variable that keeps track of the current minimum in this code. And the question is how many times is that variable updated, assuming that all the keys are distinct. So in this example, we start out thinking that S is the minimum, O is less, so we update it. R and T are bigger, but I is less, so we update it again. G, E, and finally A is the fifth update. So for this permutation, min is updated 5 times in the first pass. This quantity is called the number of left to right minima in the permutation. So that's what we want to analyze first. Now, so that's our question. How many left to right minima are there in a random permutation? Now, from a practical standpoint, this question is maybe less important than some of the others we talk about because this cost is not significant compared to the number it compares. but still it's a fundamental property of permutations that we want to study. So a left to right minima, or we call an LRM in a permutation, it's a parameter of permutation, and it's an element that's smaller than any item to its left. So if a permutation begins with 1, like the ones on the top in these examples, it's only got one left to right minima, the 1. If it begins with 2, it's got exactly 2, the 2 and the 1. If it begins with 3, it might have 2 or it might have 3, and so forth. Permutation in reverse order of size n has n left to right minima. Each new one is a minimum. And so these tables in our standard form show for each permutation the number of left to right minima off to the side. Then the total accumulated cost is just summing those numbers, or the for 3 elements accumulated cost. There's 2 that cost 1, 3 that cost 2, and 1 that cost 3, so that's a total of 11. Divide that by n factorial. The average number of left to right minima in a random permutation of size 3 is 1.833. And similarly, for size 4, it's 2.083 and so forth. How many left to right minima in a random permutation of size n? So that's our question. And again, as usual, it's very worthwhile to fully compute small values, both to get an appreciation for the intricacies of the problem, and also to have precise values to check against when we complete the analysis. So that's what this table is. So what we're going to do is use a combinatorial construction to help us derive directly a relationship that the accumulated generating function has to satisfy. And that's the figuring out which construction to use is the art of analytic combinatorics for these kinds of problems. So for left to right minima, we're going to use a star product construction where we say a permutation is a permutation starred with an element, and that gives us a permutation 1 bigger, and it has to be renumbered in all consistent ways. And that just corresponds to giving the last element the numbers from 1 through n plus 1, and then renumbering the other elements in the permutation accordingly. Now if you look at the original permutation, in this case has 3 left to right minima, all the permutations that we got from the star product have the same number of left to right minima, with the exception of the first one has an extra one, which is the 1 at the end. So that construction and that observation tells us, if we know the number of left to right minima in the original permutation, we know the number of left to right minima in all the permutations that we constructed, and that's there's p plus 1 of them, and every one of them has the same number of left to right minima as p did. So those copies, and then there's one extra one, the one that ends in 1. So that's a combinatorial construction for permutations, and then we're going to use that to derive a formula that the generating function, the accumulated generating function, has to satisfy. P plus 1 LRM of p plus 1. So to compute the average number of left to right minima random permutation, we define the accumulated generating function, which is the sum for every permutation of its number of left to right minima times e to the size over size factorial. And again, if you group the permutations by their size, that gives the accumulated cost, the exponential generating function for the accumulated cost, which we denote Bn. So now if we apply the construction, every permutation of gives us p plus 1 permutations. And the number of left to right minima in those permutations is size of p plus 1, L around p plus 1. Size of the permutations that we construct is z to the p plus 1. Applying that construction immediately applies that equation on the generating function. And that's an easy equation to simplify the first term is size of p plus 1 LRM of p, and that size of p plus 1 cancels with the size of p plus 1 factorial below the z, the size of p plus 1. So that gives us the first sum, LRM of p, z p plus 1 over p factorial. And then the second term, the plus 1, just throws out a second term with z to p plus 1 over p plus 1 factorial. So that's a simplification. Now both of those we can evaluate. The first one, if you look up at the first equation, is just z b of z. And the second one, if you group by size of the permutation, just gives z to the k plus 1 over k factorial. Z to the k plus 1 over k plus 1, because there's k factorial permutations of size k, and that'll cancel with a k plus 1 factorial, just leaving a k plus 1. And that generating function is just log of 1 over 1 minus z. So now just solving for b of z, we get b of z equals 1 over 1 minus z log of 1 over 1 minus z. And remember, that's the ordinary generating function for the harmonic numbers. And remember, our trick for permutations, if we get just extract the coefficient of z to the n in that, then we get the b to the n over n factorial, which is our average number of left-right minima, and it's just the harmonic numbers. A direct derivation of average number of left or right minima using combinatorial construction. And it's a good idea to check those against the actual values that we observed at the beginning, and sure enough, those were the harmonic numbers. It's also possible to get the generating function equation through analytic combinatorics, and I'll talk about that in a minute. But it's worthwhile to think in terms of these direct counting equations too. And we'll worry about the analytic combinatorics and parameters a little bit, mostly in the second part of the course. It's worthwhile to get a little bit of experience working with it in this form to really have a feeling for the power and generality of the method. So that's left to right minima. Now, a similar question in terms of parameters on permutations. Suppose we want to know the number of cycles in a random permutation of size n. And again, if we look at this table, the number of cycles in each one of the permutations is written to the left. And we can go ahead and compute the accumulated costs. And probably you already recognize that it's the same number. And so now we're going to look at why it's the same number. So to analyze the average number of cycles in a random permutation, we'll use this same basic approach. We'll look at a construction that that constructs permutations. Given one permutation of size n, construct n plus 1 of size n plus 1, and use that construction to rearrange the terms of the sum of generating function to imply a relationship that generating function has to hold. So for cycles, what we're going to do is, if we have a permutation that's a set of cycles, we're going to insert, and it's of size n, we're going to insert n plus 1 into every position in every cycle, including the null cycle. First thing is put 7 in the null cycle, so that creates a new cycle of size 1. And then put 7 in every position in the 1 cycle. There's only one place. It makes a 2 cycle with 2 and 7 in it. And then in the 2 cycle, there's 2 places to put it, 3, 7, 6 or 3, 6, 7. And in the 3 cycle, there's 3 places to put it, either 4, 7, 1, 5, 4, 1, 7, 5, or 4, 5, 1, 7. So that permutation of size 6, we construct 7 permutations of size 7. And so now the question is, how many cycles are there in all of these permutations? So if the number of cycles in the original perm is cycles of p, then how many are there in all of these? Well, they all have the same number of cycles, except the case where we added a new cycle by adding to the null cycle. So there's p plus 1 copies of the original perm. They all have the same number of cycles, and then there's one extra for that extra singleton cycle. So immediately now you can see that's exactly the same relationship that we had for left to right minima. And so what that means is the derivation is going to be exactly the same. So instead of LRM, I wrote cycles, but it's the very same derivation. We apply the construction and use that to essentially reorder the terms in the sum. Let's say the generating function also has to equal that expression. And then it simplifies in exactly the same way to get down to the harmonic numbers. Average number of cycles in a random permutation of size n is h sub n. Now, when we have the same generating function, again, often in combinatorics, when we see that, what we like to do is find a correspondence, between one-to-one correspondence between the number of LRM and the number of cycles. So it's a reasonable question, is there a one-to-one correspondence? And this is a famous one, and the answer is yes. So what you can do, if you have a set of cycles, you can build a permutation corresponding to that set of cycles, a unique permutation corresponding to that set of cycles, by looking at the smallest element in each cycle, and call that the leader of the cycle. So the first one, the 4 is the leader. The second one, the 1 is the leader. The singleton cycle, there's only one. Third one, the 14 is the leader, and the last one, the 2 is the leader. So we identify the leader of each cycle. And then what we'll do is write down the cycles in decreasing order of the leader. So we pick the largest leader and then write down its cycle just by following the cycle. So in this case, the largest one is 14. That's where we write 14, 16. The next largest leader is just the 5. The next one is that first one, which the leader is 4, so we write down 4, 10, 6, 15. And then the big one at the end, we write down 2, 12, 8, 3, 11, 13. And then the one containing the 1, 1, 7, 9. Now, we don't write down, we didn't demark the cycles in any way, but that's a permutation. And so I said it was unique, and that means we can use a corresponding process to get a set of cycles corresponding to any permutation. What's the set of cycles corresponding to this permutation? So we're given the permutation. What we do is identify the left to right minima. Those are the leaders. Remember, we picked the leader as the smallest in the cycle, and then we wrote them down in decreasing order of the leaders. So between each leader, say between 4 and 2, everybody on the same cycle as 4 is bigger. And so as soon as we get to somebody that's smaller than 4, that's the leader of the next cycle. So that's how we break up the permutation into cycles, and that's immediately shows that the number of left to right minima is equal to the number of cycles, because this correspondence is 1-to-1 and works for any permutation. So that's a famous correspondence between left to right minima and cycles. So now we can write down the cycles just by finding the LRM and then simply writing the cycles out as before. So that's a couple examples of parameters and permutations, left to right minima and number of cycles.